my name is Steve Arnold. I've been a Gen 2 developer for a very long time, and more recently, Yocto, an embedded developer of Inch. I have a few commits in the last couple of releases. So this is really all about kind of my current state of affairs that I've been figuring out here on my own, of where all this stuff is at. So I have a lot of embedded devices that have most of the current ARM graphics cores. I do not have a Snapdragon Adreno device, so I have never been able to test one of those. And that's one of the ones that's actually relatively current as far as what you see when you want to build Mesa and the other video stuff. If you're on an ARM machine, you get a video of Freescale option. And so that's the driver that runs on that Snapdragon. But anyways, I have several devices, one of which is now pretty much fully open source, although it's a end-of-life Tegra 20 device. So hopefully the newer K1 is going to get there quicker with the new Bow driver. So and we'll talk about that. So, how many people here have actually worked with embedded stuff? Oh, a bit more than I thought. Anybody never, ever touched it? Okay. So, in the embedded world, it used to be, okay, I'll try to go through this fast. Embedded was always kind of a really small, single-purpose machine, very resource constrained. These are a couple of the early examples that I've played with. And this was one of the intended to be hackable embedded devices that was actually really nice to use, even though it was very, very limited. Right? Not much RAM, not much clock speed, but you can sit it on the network and it runs very well. It's essentially, that one's essentially a G3 without the Ultimate processor. But nowadays we're getting really blurry, the lines between what used to be embedded and what was considered a desktop/server machine. Modern embedded devices have a lot more, especially the open source ones, they have a lot more peripheral connections that you're used to on the desktop and server side. They have a lot more horsepower, they have a lot more RAM. We're up to things like 4 gigs of RAM and 4 to 8 processor cores, right, on the newer Samsung ones. So it's really hard to tell. The main difference now is that these embedded devices are small compared to your desktop box. Even the Chromebooks are smaller than a normal laptop kind of a thing. So this is the open source Tegra 20 device. And so it's got bootable SD card, HDMI, DVI, digital audio, all that stuff. And this is fully open source, mainline kernel, no graphics blobs, no patches, and kind of a bleeding edge video driver for X.
That's X, not Wayland?
Yes, that's open. It's Open Tegra XF86 video, like essentially. So it's one of, it's essentially the equivalent of your Radeon or other XOR video driver. So it's part of the XOR video package deal. Now it's pretty raw, but it's also kind of built against the new interface, which is very good. So there's one. Well, so most of them now, they have multiple FPUs, but they're not completely Neon. Certainly is not IEEE compliant math-wise. So you have to be kind of careful about the data that you feed it and make sure that it's solvable, essentially. So you have a VFD for each core. Some of the GPUs have a lot of cores. That's kind of the latest one. So it's really approaching desktop class stuff, just in a very small form factor. Here's another hat. IMX6 quad, running off an SSD. So, and the same thing, HDMI, USB 3, yada, yada, yada. All the current peripherals, pretty much. So, ARM v7 HardFloat is kind of the current standard as far as sort of hardware capability and compile switches, things like that. There's a couple of newer VFD definitions. There's a VFD4 that's not as common yet that you see on the newer ARM boxes. So these are what we're looking at. This is a wanboard inside here. The udoo and Qbox I are all the same ARM core and very similar GPUs. Beaglebone Black is a TI OMAP with your standard SGX PowerVR graphics from TI. There's a lot of these Sunxi Allwinner Rockchip. They all run off this same kernel. And these guys are pushing as many device tree definitions into the kernel as they can get in now. There's several patch sets doing that are like in various stages of working their way into the mainline kernel. But right now there's probably a couple of 3 or 4 of those machines that are good enough to build now in terms of what's in the current kernel. Samsung makes a bunch of stuff. Samsung Chromebook, all your tablets and phones. They have, the old Samsung Chromebook uses the Mali GPU, which is the same as the one you find on all of these guys. So driver-wise would be the same. So on the Tegra side, it's the TK1 is the kind of latest and greatest Chromebook processor that you can get, and it's very nice, very fast, and very cheap. Genesi kind of didn't push some of their original Freescale stuff very far, so the one that I have is end of life and has a completely closed source graphics chip, so most likely will never ever see open source light of day. But it does at least have a current Ubuntu release for it. So. Now there are a few ARM v7 devices that have VFP but no neon. And so that's basically a compile difference. So if you had compiled your ARM code for neon, then it would run here. And then of course
what is neon and VFP?
VFP is vector floating point, which is kind of the standard ARM floating point processor, and then Neon is a SIMD. What's the acronym? Neon is essentially a faster vector processor, but it's not quite fully IEEE math compliant, so you have to be a little bit careful about it. It won't give you a proper not a number answer the way that IEEE says you should.
So in the previous slide you had VFP / neon.
So that means it has both.
Does it make sense to vector floating point?
Whether it makes sense or not, I'm not quite sure, but that's basically that's a standard hardware implementation on the ARM side. So, but like I said, the Neon is quite a bit faster at what it does than VFP. But VFP is actually compliant, whereas Neon is not. Yeah.
What's the difference between VFP, Neon, and Ultivec on machines?
So AltaVec is of course a different implementation, but it's similar in concept to the vector floating point on ARM. I think performance-wise, I'd have to go research a little bit. But I know that the older G3 PowerPC stuff that did not have AltaVec was potentially quite a bit slower for certain processes. So it's essentially, I mean, every architecture has its own math coprocessor ideas. And so they have on the x86 side, they have their version. On the PowerPC side, they have their version. On the ARM side, they have two. And of course, Raspberry Pi is kind of the low end of these things. It has the newer Pi 2s are ARM v7. So you'll get Neon on those. But the ARM v6 is kind of one of the older ARM implementations, and it's essentially, I think, what's in an iPhone 3 is an ARM v6. So after that, they went to ARM v7. But so this is basically the hardware that I've been building and testing on for the last several months. Actually going back probably a couple years if I go back to the first Chromebook that I bought. So state-of-the-art graphics, you can get pretty close. So in terms of vendor blocks, these guys are kind of all over the map with which kernel version they're stuck on and what kind of vendor proprietary stuff that you use to make it work. So I tend to only test this stuff lightly just to, see what it can do, and then I tend to wipe it out and go open source. And so I might keep around like a bootable SD card with the vendory stuff on it, or occasionally like on the Chromebooks, I just have Gen 2 running with the vendor kernel because it tends to make things a little bit easier. So, but on the open source graphics side, we do have some that are either very close or almost there in terms of having enough open source functionality to be able to get by without that stuff. So I think the one that I told you about here, this guy, the OpenTegra one, is probably the closest one so far that I've gotten fully built and working. The Nouveau one, I just got the K1, so I haven't gotten very far with that yet. Just enough to sort of build up a couple of Gen 2 root FSs and see how it performs as a DCC helper. But it's essentially a GeForce graphics processor. So it is compatible with Nouveau. And there is at least one upstream Linux for Tegra. So the L4T Linux for Tegra is the upstream lobby stuff for this. And there's one that's almost open sourced and that I'm getting ready to test. So these are the open source driver clones or re-implementations of this stuff and what it's possible to actually run on the device depending on what you're trying to do. And like I said, this is the one I don't have any hardware for, but it's been in Mesa and some of the other things longer than the others, so I'm going to say it must be more mature. So I haven't yet gotten to the EtnaViv driver, although I have FB Turbo running on that guy with an X desktop. The OMAP FB is the TI. Which one is the TI? Yeah, the OMAP FB. OMAP. There's one of them that comes out of the Power VR stuff from TI, and the other one's open source. And there's 2 open source ones. But mostly on the beaglebone, I run the console stuff anyway, so I've only done a little bit of that. But so the FE Turbo runs fine on Mali, and fine on the Vivante, at least well enough to use. And FE Turbo is pretty standard on Raspberry Pi. So that's what you get in Raspbian and the other ones. Although what you can do is switch to that. You can switch to a Wayland-based shell that's very immature yet on Raspberry Pi. That actually does use the native video scaler and no proprietary stuff. So Raspberry Pi is kind of close, but not. There's nothing for X or anything like this. Wayland Weston based, which is another thing I'm kind of interested in testing, so I sometimes get sidetracked with that a little bit. So when you look at what you get from upstream with some of these things when you buy them, what you end up with, even if you want to build out of their kernel repo, what you end up with is a single kernel branch. No other versions in their repo that you can switch to, typically. They may be working on forward porting their stuff to a newer version, but generally they sit on the same kernel version forever and ever. So it gets a little weird when you're trying to upgrade all the other software around it, and you can't do anything, with what they have as their kernel. So you can try sort of backporting some stuff from newer kernels yourself, which gets a little weird also, unless you're a kernel developer. If it was that easy, I think the upstream vendors would do it a little bit quicker. So, like I said, it can take them quite a long time to start to forward port their stuff to a new branch. So the oldest kernel I have running is on that end-of-life SmartBook. It's still on 2.6. And they never ever bumped anything newer. But I think 3.14 is the current Yocto kernel. So if you build several of the ARM devices in Yocto, you'll get 3.14 automatically. The newer versions they have as the Yocto reference kernel are not yet configured to build for anything but a Gene machine. So you kind of have to force upgrade Yocto if you want to try it. But that is a less than optimal kernel for beaglebone anyway, so. And so when you try to start playing around, if you want to build your own version of the upstream kernel, you can still run into trouble. And it seems weird because if you're used to building your own kernel fully open source, you don't have build problems anymore. And you don't really have configuration problems where that you have one or two sort of really wild minor ones, but on some of these vendor kernels, they break quite easy. And so if you change the configuration in one place, just one little thing, sometimes you don't get even a build, right? So they tend to get a little brittle the more that they keep patching and patching and patching that single version. And most of them are not yet on the device tree train. So the older vendor kernels are typically the legacy driver model. And so that makes it a little bit tougher for people to integrate with newer stuff. So, and other things that you'll see, a lot of things that they tend to build monolithic kernel configs as their kind of desk config for that machine. And so a lot of stuff you can modularize, but a few things you can't. And you don't know it until you try to do it and it doesn't work. Because in the kernel, of course, it says, if you want this as a module, put M. But some things just don't like being a module. And then some of the dev configs will end up missing one or two kind of key configuration options that you might want. So that should be the first thing that you look at. If you build one of these kernels and suddenly your USB doesn't work, then go back in and look at the USB config and make sure they didn't screw something up. Let's see, general config changes. Again, you just need to be a little bit more careful than you're used to with an x86 kernel config. Because like I said, they're very sort of, there's a lot more interdependencies between config options in this world than there is in the x86 world. So current vendor blobs in the QBox I are actually fairly recent. Their kernel is more recent for some reason than the other IMX4 guys that I have, so that's not a bad one to start with, even if you don't want to mess around and go open source. The Raspberry Pi has at least opened their documentation. Well, the Broadcom has. And so you can talk to the video scaler directly and things like that, which is what the Weston, that Maynard shell does. And it's not quite, I mean, they're, just because they open source, open the documentation doesn't mean that it's going to instantly have all this wonderful software for it. It takes a little bit of time for people to crank some of that stuff out. But so all these guys are going to come with their own, basically their funky kernel version and their funky vendor stuff. But so, like I said, in here, on the open source side, this is more or less kind of the order of level of integration in terms of the open source stuff. Although I left Arduino at the end, so I don't know what that, I don't know how far that is at all. So, the two ones that I would recommend now would be the Tegra or the Raspberry Pi, as far as playing around with the latest and greatest open source video stuff. But maybe when I get to the Vivante stuff, we'll find out some of that's a little bit better off. I don't know. So okay. Okay, now here we go. So again, too much of that. Did we already go? How can we go backwards on that? Okay, there we go. U-boot forks. That's the other piece of it. So every one of these vendor guys typically has their own fork of U-boot. And if they're on the ball, they might have basically a newer branch that you can switch to that's essentially the upstream U-boot. So, and that's usually the difference is device tree support, right? The kernel device tree stuff, if it's not there, it's one version of U-boot. If it is there, it's a newer, closer to upstream U-boot. So, but everybody eventually tries to converge with the upstream guys. And so the closer that you get to that, of course, the fewer weird patches you need. A couple of them are odd, right? So Chromebooks are a little bit weird in the way that they partition and boot stuff because they have kind of a secure boot feature, yada yada. You have to put it in developer mode to do anything. But mostly the other ones are vanilla U-boot. That a lot of the newer kernel brand, the bleeding edge kernel stuff being maintained by a couple people It's up to, it's basically 318, 319, vanilla U-boot with very, very few patches. So it's about, there's kind of half a dozen to a dozen machines that have the bleeding edge stuff already in place. And so we'll take a look at that in a second. So, but the common deployment for most of these newer things is basically a 2-partition SD card / flash setup, where the boot partition might be ext2 or even VFAT in the case of TI, and then the root partition ext4 or whatever you want. But essentially you just copy the U-boot image to the U-boot partition, and then he looks for the kernel based on the default config either compiled into U-boot or what he reads. You know, there's U-boot logic that you can write a little uenvironment.txt file to redefine some of the variables and give it your root FS and other arguments for the kernel. It's kind of what replaces the old boot script U-boot thing. So it's an easy manual deployment thing. In some cases you can get systems like Yocto to build an SD card image so that it's all done for you and you just feed the image to the card. But most of the time with the bleeding edge stuff, you're making it by hand. And you can see a lot of that here. So the elinux.org has a bunch of device tree stuff that you can go ahead and go read about device tree stuff. It's specific to ARM, but it's kind of critical. So you need to actually deploy the device tree blob along with your kernel image, unless you build it in. I don't typically build it in. But the other guy, this eWiki Linux on ARM, is where you can get several how-tos on what I've been talking about, deploying kind of the bleeding edge kernel and U-boot stuff to your device. So he maintains the patches for both. Well, if there's a U-boot patch, he maintains that, and whatever set of kernel patches are needed for the latest upstream kernel. But that's how I run 318, 319 kernels on several of these devices. This is one of them. There's something here. It slipped too far in my pocket. Okay. So it kind of depends on the latest stuff. Each one of these machine-specific kernels is different. I mean, each one has its own set of patches. And so, but he takes care of all that stuff for you, essentially. So you don't need to do it much by hand, because he maintains the repository with patches and build scripts for a bunch of these machines.
Is this Robert Nelson? Who's he?
Yep. Yes, he is Robert Nelson.
Okay.
Sorry, it's not in the URL. I thought his name was in there, but it's not. So yeah, Robert works at DigiKey, and I haven't yet asked him why he does this, but but I'm glad that he does. I got to meet him last year at Embedded Linux, so I've been using his stuff a lot. So, but essentially all that ARM device tree stuff is in process right now. For these vendors, they're pushing patches literally as we speak, pushing patch sets of new device tree stuff, their devices into the kernel. Hopefully some U-boot stuff upstream. So this is really, really ongoing right now. Like I said, if you go to the eWiki site, there are several different machines, a handful of vendors, but there are several different Freescale TI at-mill machines. If you want to go buy one and play with it, maybe you want to pick one off this list. So beaglebone's not a bad one, 45 bucks.
Robert's the guy that actually makes the images that ship on the board.
On which?
On the beaglebones.
Oh, yes?
Yeah.
Well, if you would know him, I would think.
Yeah, I know him.
So I'm just glad he has that stuff in public and that well documented.
Yeah, he's incredible.
So I think I had the same title on too many slides. But anyway, so free and open source graphics drivers. There's a really nice Wikipedia article. And we can actually look at some of their graphics because they're awesome. Creative Commons licensed graphics. So let's look at, here's the kind of old, well, this is where we're going. How about that? Let's start with this one. So this is really kind of where it's going, I believe. So this is not the current state, but it almost is in certain places. Right, so what we're talking about essentially is a re-architecture of the kernel, DRM, and graphics interfaces for all these standards and whatnot. Right, so the architectures for everything is kind of moving to this Gallium 3D state tracker interface. So right now it's quite a bit more scattered. Lovely Ubuntu. This is my spare laptop. My Gen 2 machine has a video problem. So let's go. There's one other one here. But I encourage you to go read this. It's a pretty interesting article if you want to know about what's going on that side. Here we go. That's what I was looking for. So the intent is to provide interfaces that both proprietary vendors can use and that open source drivers and applications can use. So this is sort of the old scattered way to do it. Let me see, what are we looking at? So well, I guess that's not working so well. But anyways, that's kind of the reason why that a lot of this stuff is in kind of what appears to be an unknown state when you first look at it, and it doesn't make a lot of sense because like everything is different. Every vendor is in a different place. They all have their own stuff. They all claim to support, the hardware level supports this stuff, but not the software level yet. Or at least not in an open source way. So it should be getting better as time goes on. And like I said, everything is sort of moving away from the legacy driver model and a better abstracted interface. So maybe by the time I get through a couple of these untested drivers, it'll be in a better place for me too. But this is kind of where I'm at as far as that and kind of level of testing. This is one I have that's got the most testing because it's one that has the longest. And then the Nuvo stuff is brand new, so I just got started with that. I've kind of given up on this one. That was one of my original ones. But that was before the Chromebooks were available. So. And then, like I said, when I get to around the packaging, these two, they'll be in the ARM overlay for Gen 2 on GitHub. And then eventually, hopefully, into the tree. So for vendor OSs, I mean, it's not like the options are horrible. For most people, they'd probably be just fine. And depending on what you want to do with it, but things like the Q-Box make the perfect, box on your TV kind of thing. You can stick with the vendor OS if you want to, unless you have a problem. But some of the vendors actually give you quite a few different OS options. Some of the vendors don't kind of give them to you, but you get them anyway, because people do it. So on Raspberry Pi, if anybody chooses the noobs thing, it lets you actually select the distribution that you want to install from the card itself. So you put the noobs on the card, and then you get to pick your OS. beaglebone has a lot of separate images you can download, various Linux flavors. Gen 2, of course, you have to build yourself. The Chromebooks are not that, well, Chromebooks are supported by Crouton, and there's a Ubuntu script that will automatically install Ubuntu on your Chromebook, either SD card or SSD. So that's a pretty easy way to get Linux on your Chromebook. And you can do it manually and pick your own distribution if you want to. So there's a couple of, Google is your friend, there's a few Gen 2 developers that have written up various things on how to do Gen 2 on XXX. And a lot of times you just do it the same way anyway, right? So somebody's written a thing on how to do it here, and you got a different device, but the procedure is basically the same. And the udoo one, that was a Kickstarter project. They started out pretty bare bones, but when I went back and looked, now they have a ton of stuff. And it wasn't that long ago that their Ubuntu 1.0 came out, and that was about all they had. So you can have several different, even non-Linux OS. They have some implementations of RISC OS you can put on some of these machines. I'm not sure, OpenELEC and XBMC are kind of more or less the same things. The same sort of media center distribution. So, flip a coin, pick one. But so if you want to build...
XBMC is not a distribution.
Pardon?
XBMC is not a distribution, it's a package.
Well, right.
Like is a distribution.
Well, okay, but there is that's right, the other one is Raspbian. No. There's Raspbian one with XBMC. Right, so it's Debian with XBMC. Right, the other one's OpenELEC with XBMC. For building bootstrapping, you have a couple different options. Mostly the build from source stuff takes a little while, but it gets you a lot closer to what you want if you want something custom. Otherwise, it's pretty easy just to do a Debian bootstrap. But you do need, for Yocto, you absolutely need a BSP layer for the machine.
What about ARM, Arch Linux ARM? Do you have any experience with that?
I don't personally, but it's generally one of the options that you have on these guys for doing it manually. A few of them, they might have an Arch image. You have to look around. But Arch is certainly in the mix with a lot of these machines, and it is an option. So, Yocto, you can build an image, lots of images for your machine if you have a BSP, or you're willing to go through the Yocto BSP developer manual and create one. Depending on the machine that you want to create one for, it might not be that hard. A lot of the information is already available. It's essentially creating a config file and making sure that you have the right kernel version in your BSP layer plus uboot. And you can build that image on a desktop machine really quick compared to building Gentoo on some of these machines. So Gentoo gives you the stage 3 that you're supposed to use to bootstrap your install, but it'll run by itself. You don't need a system logger or the other stuff that you add on top. The stage 3 will just boot if you have a kernel and bootloader. So that's sort of the quick and dirty Gentoo install on a lot of these machines. You steal a kernel and bootloader and you put a stage 3 on it and boot it up. And sometimes you just steal it right off the card that comes on the machine, right, that came in the box. And then if you're lucky, you can switch to a Robert kernel and get a newer one. So this is the manual way, but it's also a very good learning way. But if you've never done Gentoo, well, it wouldn't be all that different. If you're willing to learn, it's a great way to do it. So, but it does help to have some x86 Gentoo experience before you start doing this. So, but you do have options here. I build ARM stuff in a VM, like Raspberry Pi on a quad-core ARM. Makes it a lot faster. I'm sorry, CHRoot. Sometimes I build in a VM on a Gentoo box because on Gentoo AMD 64, Yocto has a live sudo problem. So sometimes I just spin up a VM as a small build environment for that. Let's see. So, oh yeah, you can look at, there's a Gentoo embedded table on the wiki that people put all their devices in. So if you want to do Gentoo, you can go and look for your device and see if it's in there, and then you know who to talk to on IRC. And then of course you can always pretty much debootstrap a Debian install. If you can boot it, you can debootstrap it, which is their tool for bootstrapping a Debian install. And so I do that once in a while. So deploying, basically, it's what I talked about before. The Gentoo deploy step is really easy. But so as long as you've got, first you need a bootable disk image for the device, and generally that's the vendor stuff, unless you just download one from some other developer that's already done it. They won't stay. So bootable disk image will give you actually most of the time you'll be able to steal the bootloader and kernel right off that disk. So, but basically you mount, and you could mount from your device and CHRoot into your own tree to start building stuff if you're doing an Gentoo kind of a thing, or CHRoot into a bootstrap. But essentially most of these machines boot off an SD card, and so it might have an internal flash or SSD or some other thing with the vendor stuff on it, but you can just boot it up off the SD card and play around with your own stuff and not worry about touching the vendor install that's on there if you want to preserve it for your kids or whatever. So go ahead and boot up and work on an SD card. Some of them are actually not that slow. If you get like a Samsung Ultra, that's reasonably fast. But disk I/O is an issue with some of these things because card disk I/O is inherently slow. So you will see things bogged down. That's why the SSD makes things quite a bit faster. So, yeah, like I said, basic steps, very easy. Is something wrong with this thing? Okay, that's pretty much it. That's crappy. Hello. So, questions? You guys look tired. Yeah, sorry.
Do you find that the pace of development of these chipsets is kind of outpacing software in an expanding way? For instance, every year a new chipset comes out that's new and exciting, yet it might take 2 or 3 years for open source.
I think that is kind of exactly correct. Because when you look at what the vendors claim their GPU does and supports, it's generally looks a lot better than what the software support actually is. So they do support the latest standards, GPU is capable of doing all this stuff, but there's not enough software out there to actually make it do all that stuff. Certainly not enough open source software. Yeah.
You touched upon the varying states of different open GPU drivers on ARM, but on ARM you also have hardware codecs on the SoC, and can you expound on like the states of different free and open hardware codec drivers for the chips?
That I haven't really touched yet, but you are right that in some cases, at least on the Raspberry Pi, the codec stuff should still work. I mean, that's where you need you have to put in your key.
From what I've seen, most of the chipsets, I mean, they're binary-only drivers for the codecs.
Okay. Well, if that's the case, then you might be SOL.
IMX 6 is like that.
Is
For
it?
the GPU, yeah, you're stuck on their vendor kernel, same way.
Well, then
Require
you
those
want to
features.
choose a vendor that has a newer one, like Qbox. There are several versions ahead of like the udoo guys. So.
Yeah, if you need the full set of them, you're stuck on their 310 or 314 if you're in their partner program.
Ah, okay.
Yeah, they do early access for people too.
Yeah, I kind of tend to. I'll go here for a second. You were right.
Yeah, have you ever tried using CrossDev and Gentoo to build the rootfs?
I don't do the whole rootfs that way. It works for most of it, but it's easier to just do it native when you have a couple dozen ARM cores and just CC. It doesn't really take that long. I use CrossDev to build tool chains a lot, but normally I build kernels and bootloaders with that. And that's essentially just to get things bootstrapped.
Yeah, my question was about some of the FPGA chips that have also been including ARM processors on them as well. Have you had any sort of experience working with those, and like, are they kind of encountering the same sort of issues that?
Do you have an example?
Like when the chips coming from National Instruments per se.
Well, I mean, the FPGA stuff that we've worked with has been basically separate modules, not integrated directly onto any of the ARM devices that I have.
Oh, okay. So you just haven't had a chance to get your hands on any of those yet.
Right.
Xilinx has one. Was that for?
Got one of those yet?
No.
So, but I mean, I would hope that the FPGA interface would not have this kind of issue, because an FPGA is just a generic thing. You load your HDL code in. Of course, they could have some kind of proprietary thing involved, but I would hope not. So that's certainly an issue that you want to research if you're thinking about doing something like that. That's a very good question, but yeah, I need one of those devices, so it's much easier to test stuff that you have in your hand.
Yeah, I just haven't really seen anybody try and load Linux. Well, actually, the ones from National Instruments come with their own version of Linux, but it's got their own Pascal kind of kernel on there.
Does it?
Yeah.
Well, the Xilinx ones have a kernel driver, I believe, in mainstream. right? So you can look, there's some of the FPGA interface stuff that's already in the mainline kernel. So maybe that's, if you want to buy something, maybe that's what you would start with. So I believe there is a Xilinx.
I haven't looked at it, so.
Okay. Look in the config for like 318, 319. There's this Xilinx like firmware loader module. Yeah, question?
Oh, I was just wondering if this situation was comparable to, say, TI and OMAP and all of the co-processors, like they run some of those codecs. They've released some DSP support for developing firmware for the DSP cores that are also on the SoC. It took them quite a few years to get development support out of their proprietary tool set and start to have some open source development options for some of those alternate cores.
Right, that is true, and so the DSP stuff on a lot of the older TI boards, I would think, would be a little bit less accessible. There's no DSP on beaglebones, but it has what, the MPU stuff, or what? PRUs.
From what I understand, the free and open tool chain that was released for TI's DSP were for their earliest DSPs and not any of their later ones.
So I work for TI, so full disclosure there.
That's Jason, by the way.
There's a full GCC for the C6000 DSPs, including updates to some of the newer ones. So
that's a replacement for the TI tool chain for that CD.
Yeah, if you don't want to use the TI tool chain, you can just use the GCC.
Okay.
So for the DSPs that are on the beagleboards, the beagleboard and the beagleboard XM. For the ones on like the beaglebone, the PRUs, there is a GCC that somebody did based on the FPGA, on these synthesizable FPGA cores. They took that as a base to create the GCC for the PRUs, but I haven't had a lot of feedback from people that are actually using it. So if you don't want to use the TI tool chain, which is finally freely redistributable but still closed source, then you can use that GCC for the PRUs.
So does the GCC CGT stuff support more than just beagleboard, or is that kind of unique to each one?
The C6000 stuff also supports boards.
It's on like the
so there's other DSP boards where you can actually boot and run Linux. So the part of it was, in order to have support in the mainline Linux kernel, you have to have a GCC compiler, because that's the only way the patches will be accepted.
Right.
But there's actually mainline support for C6000 in the Linux kernel. So you can actually boot and run Linux, MMU-less Linux, on C6000 devices. So you can actually run Linux on those DSP cores, including like C6000 DSPs that are standalone and not run on the beaglebone.
That was the same tool chain that they were providing for like the DM8168 valve stuff, and so the GCC will work there too, right?
Yeah, it will.
Are you familiar with the TI DSL chips that were sold off to Infineon?
I didn't know where they were sold off. I did do some work on the DSL chips in the early days. So.
Right, but they have those generations of DSPs.
Yes, that's the original C62. That's the C6200s, and those are supported in the GCC.
That's interesting. Because
that's older, and that was never really super high quality.
But that's what was used when the chips were in TI before they became Infineon.
Yeah, well, that's CPU cores still supported. But there's over the last 3 years or so, there was funded work for I believe it was Red Hat or to actually work with people that really knew GCC to actually get the VLIW stuff, which is the hard stuff, because it's a very different CPU architecture. It's not RISC, it's VLIW, and to get that stuff to optimize pretty reasonably. So the original C6200 stuff that's been there for years was never able to produce really good quality code. That's been completely changed over the last 2-3 years.
That's good to hear.
Yeah. So now in GCC, there's actually good quality C6000 compilation.
Interesting.
So, for a lot of people, maybe some of those esoteric DSP parts wouldn't be so important, but for some people they are. And so that is very good news that you can actually replace the code generation tools with GCC. Well, that's pretty much all I got. If nobody has any more questions, you can find a lot of this stuff on GitHub. I keep as much of the latest stuff in the ARM overlay we have on GitHub for Gen 2 as I can. And so it'll get pushed into another Gen 2 developer overlay and work its way into the tree. Unless I want to really commit something like right now. But I tend to let other people play with it a little bit first before I want to push it into the public arrangement. But so that's where you'll find a lot of this stuff, either in Yocto layers or Gen 2 overlays. Thanks.